Well, thanks for putting pressure on me to come up with an exciting talk here. So I'm going to talk about why all those little ciscoes, and there were a lot of them. And it was what we saw, most of us think about cisco. We also saw that was true for bloater, and it was true for chi, just pretty much astronomical numbers, the biggest that we've seen since our standardized surveys began in 1978. And those two maps are there. The upper one is from 2022 year class that we collected in May of 2023. And so those three species were caught across the lake, and they were caught where they should. Bloater out in the middle of the lake, or excuse me, chi out in the middle of the lake, and bloater and cisco along the shore. And just for comparison, 2017 is shown there. So if they're not there, we don't catch them. If they're there, we catch them. If we're not, we don't. And the simplest answer is they didn't die. Their younger selves didn't die. And it sounds smart aleck, and those of you who know me, I like to be smart aleck, but it's unintentional here. We've been collecting larvae for 10 years, and we do it at the same time that we bottom trawl on these surveys, so we basically get these data for nothing. And for the first 10 years, I did not understand what the population dynamics part of it was trying to tell us. We couldn't figure it out, why they were high, why they were low. And so what I know today is, in May, it's dependent on what kind of winter or spring it was. If it was cold, then we didn't catch any because they hadn't hatched yet. So our survey is timed for when they're hatching, but if it was cold, then they hatched late, so we didn't begin to catch them. So those numbers in May are really low, and if it was a really warm winter, they hatched early, and so those numbers are really high. So it didn't tell us anything. And in June, the numbers were equivocal, and they didn't relate at all to the little bit of recruitment that we had over that 10 years. So you see in 2022, those blue bars, they're similar as all the other years for June. And the revelation came in July, because typically they die off between June and July. And in 2022, they didn't die off. So we had really high numbers. Their populations only decreased by 25%. So in a nutshell, having those larvae live is what led to having all those age 1 fish. So why did they live? I'm going to show you a series of plots that look like this. So these are daily water temperature values derived from the satellite, so we get one temperature for each day. Each line is a year. So temperature on the Y, date across the X. All those years in 2022 in blue. So in September, there was a National Public Radio interview with Jay Austin from the Large Lake Observatory at UMD, and he talked about, it was really surprising, the temperature regime in 2022. And he was surprised by two things. One, it was really cold in June, and we didn't have a lot of ice. We had a fair amount. We had 80% maximum ice cover that previous winter, but it wasn't a crazy, like 2014 amount of ice. But we still had a really cold spring, and it was the second coldest on record. And so there's only one line in June below that blue line. And the second thing that happened, we had really rapid warming. So we went from 4 degrees at the start, middle of June, up to about 17 in September. So that was a really fast, rapid rate. And so I said I'm going to emphasize water temperature regimes. So that's got to have something to do with why all those fish survived. You can surmise from that. So there's two options here. We can have a cold spring, or we could have that rapid warming. One of those probably led to survival. Same plot. Here we're superimposed the USGS age 1 cisco index, colorized over each one of those. And the darker the color, the higher the index value was. It's not that important to get a lot out of this, other than you can see the technique that I used here, and to see how skewed the data is. So we have 45 years of data, so it seems like that would be a lot to try to understand, but about half those or more of those values are 0 or near 0. So they're highly skewed, so that makes it difficult. So let's simplify it and just look at 1984 and 2022. And these were a magnitude higher than any other years. And so if you look at these, there's nice overlap there in February, nice overlap there in June where those lines converge, and then up there during the summer warming rate as well. So that's not really telling us a lot, it's just telling us the same thing that I explained on the previous slide. So now, let's expand that out. So now we got the top 10% of those 45 years, and this turns out to be 6 values where we had that index value greater than 100. And here I see the most convergence right around here in spring, and a lot of divergence here during where we would measure the warming rate during the summer. And now let's get a little bit more quantitative and get away from just looking at something visual. So we're going to run a CART model here. And so what we're trying to explain, this is that age 1 index value, and we're going to use environmental variables that were all derived from a satellite. So now we have consistent spatial coverage, which I think is good, and I think that spatial coverage for these environmental variables fits the data that we collect on age 1, it's just our survey design model. And it doesn't matter what these things are, but see, some of them, for all of them, you have a Y value, and then you have year across the x-axis. So we're trying to get this, where we only have a few high numbers. And like something like ice, we have a lot of interannual variation, which is something that you would want. And then other ones like chlorophyll A, very little. Summer temperature, there's some, but the range is not that high. So what we got was we got really good similar spatial coverage, but we lost a little bit in terms of the range of those data values and when each year started. So we lose some of the explanatory power of those variables, like if they didn't start till 2003 and we're trying to predict back to 1977. So that's true with chlorophyll. We run the CART model. The first predictor that comes out is June water temperatures. So for those 6 values of when we had a Cisco index greater than 100, all 6 of those years, June water temperatures were less than 5 degrees, 100%. And then the second value was ice in February, and it turns out that early ice is good, but the June temperatures weren't dependent on it, and it wasn't that explanatory. So if you look at this plot here, so you got that line, the horizontal line is at 5 degrees, and then that block is at 75% ice cover in February. And so all those high years, which are shown as the blue dots, the water temperature in June had to be less than 5 degrees, but ice didn't have to be greater than 75% in February, and also having a temperature in June of 5 degrees was not dependent on having ice in February. So store that in your head. Take a bigger slice now. So now we're going to look at if that index was greater than 15. And this gives us 11 years. You see, pretty tight there. And also winter, there's not a lot, not as much variation, excuse me. Run the model here, and same first variable, June water temperatures, and it was 73% of those years. And then the second factor was clouds in July. This is something that we were now able to put in that model because we had that satellite-derived cloud data. And it was, if it was clearer, it was a little bit higher versus cloudy. And that has some implications for, I think, what some people are thinking about, or what might determine larval survival. If we're convinced now that June water temperature is important, let's look at the trend in June water temperatures, and so we can think about how they might occur in the future or not. So prior to 1998, and this is that regime shift that Van Cleve and John Lenters published on in 2003 from her master's project, that prior to 1998, a temperature of 5 degrees in June, that occurred almost all the time. Since 1998, when we've had that regime shift on Lake Superior, we have only gotten June temperature less than 5 degrees twice. and we had that 20-year gap. So that was 2003. That was a high year class for Cisco, and then that's 2022. So not very often. And then we had a couple years where we had greater than 15 there, and there when the temperature was above. So it's not just June temperatures, and it never is just one thing in life, but June temperatures have really kind of opened my eyes of what has popped out, having run these models for probably a decade now. And let's just take a quick look at bloater, because I'm sure you're all curious about how chubs did if you run that same model. And we get the same first factor, June temperature less than 5 degrees. And clouds in July came up again. It was just a little bit different value. And one thing about clouds is it's always cloudy on Lake Superior. You know, and if I didn't point it out when I showed you those annual ranges, but across that time series that we have for cloud cover on Lake Superior, the spring average varies from around 40% to 65%. So it's not a huge range. So when you think about how explanatory that could be, or what mechanism it's causing, that's a tough sell to me. But one thing that this plot does nice for bloater is it appears that June temperature of 5 degrees there's a threshold response. And so everything is to the left when we have, so this is bloater, the age 1 index for bloater, and it gets higher there, but it doesn't there's no relationship here. So if the temperatures were 2 degrees, bloater recruitment wouldn't have been higher, but if it was more than 5 degrees, you pretty much got a 0. So the next thing that we wanted to look at then was what predicts a June temperature less than 5 degrees. So we run that same model with the same variables here. And what came out was ice, and ice would be expected, right, if you had ice cover. What was surprising to me, that it wasn't very high. So if April ice was greater than 10%, so lake-wide coverage of 10% or greater, you needed that to get a June temperature less than 5 degrees. Make sense? But if you look at, so there's two comparisons here. This is the maximum ice in 2014, which occurred on, I can't read that date, but near the 1st or 2nd. And then 2022, a huge difference. And actually in 2014, the water temperature was 5 degrees. It didn't even make our model because it was less than 4.9. So that much ice in 2022, and we had a colder June than we did there. So it's that local weather pattern that seems to be also affecting June temperatures. And then clouds also was in this model. I was just shocked that clouds came out because it was something that we tried to get data on for a while, and it took a long time to find a data source. And again, it was less clouds in February, but that would just, I think, be clearer, and you might have greater ice formation. So that looking forward into the future, like the two nuanced questions are, in my mind, is how much of an age 1 index of recruitment do you need to have to maintain a fishery, and what is that number if we get that number occurring maybe every 5 years, every 10 years, or 20 years? You know, because we had that 20-year gap that I showed you in those June temperatures, right? And those are the only relatively decent year classes that we've had. Was 2003 and 2022. And these fish, once you get a good year class, they're staying in the fishery for 20 years, but you're going to need a value up around 100. And so this is some of the modeling that we're doing now, and Jeremiah is going to talk later is doing. It's just trying to quantify what that index you need and the frequency that you need it to maintain our fisheries. And then the second thing is how often are we going to get those anomalous things? And that data that I showed you previously, probably not very often. And this just, again, those pink line is before 1998, and then the green are after. And there's a nice distinction there. So we have a different water temperature regime that we're dealing with. But as 2022 pointed out, you still can get a great lake in terms of environmental conditions to get survival, even without a ton of ice, or even without a recent track record of getting that. Thank you.